You know that sour tang of lemon or the feel of soap when you wash your hands? Well, it turns out our world is shaped by this constant, invisible battle. This is the story of acids and bases, the chemical opposites that define pretty much everything, from our bodies to our planet. Let's dive in.
All right, so think about this for a second. A lemon, a bar of soap, and the world's oceans. What on earth could they possibly have in common? It kind of sounds like the start of a bad joke, but the answer is actually this fundamental chemical duel that's happening all around us and inside us every single second. Okay, so it's time to meet the two main players in this chemical showdown. In one corner, you've got acids, and in the other, you've got bases. These are the fundamental opposites we run into every single day, whether we realize it or not.
Let's make this real. On one side, you have your acids. You know that sharp, sour taste in lemons? That's citric acid. The bite in vinegar? That's ethanoic acid. Even vitamin C is technically an acid. Who knew, right? And then you have their total opposites, the bases. They're usually bitter, kind of soapy to the touch. We're talking cleaning products, baking soda, even the stuff inside batteries. So yeah, two totally different teams with completely different vibes.
So what actually makes an acid an acid? Well, chemically speaking, it all comes down to this one tiny little particle, the hydrogen ion, or H+. See, when an acid hits water, it lets go of these ions. And these guys, they're basically just free-floating protons. And that's what gives acids all their power, including that signature sour taste.
And what about the other team, the bases? Now, when a base can dissolve in water, we call it an alkali. Their signature move, they feel really soapy. And if acids have their H+ ion, while alkalis have their own star player, the hydroxide ion, or OH-. It's the perfect chemical opponent.
Okay, so now we know who they are, but here's the thing. Not all acids or bases are the same. Some are gentle enough to eat, but others, whoa, they're seriously dangerous. So we're going to need a way to measure just how strong they are, like a chemical ruler.
And yeah, this brings up a pretty big problem. I mean, obviously, tasting some random chemical to see if it's sour is a horrible idea. Just don't do that. And the source material points out that strong alkalis are caustic, which is just a fancy word for burning, so touching them is just as bad. We absolutely need a safe, reliable way to figure this out.
And that's where this comes in, the pH scale. It's our chemical ruler. It goes from 0 to 14. Right there in the middle at 7, that's perfectly neutral. Think pure distilled water. Anything below 7 is an acid, and anything above is a base. But here's the part you really got to get. This scale is logarithmic. What does that mean? It means a pH of 2, like that hydrochloric acid, isn't just a little stronger than vinegar at pH 3. It is 10 times more acidic. Every single step down is a 10-fold jump in power. That's a huge difference.
Now here's a super important rule you have to remember. You can't just take a pH meter, stick it into a pile of powder, and expect to get a reading. It just won't work. And why is that? Well, because pH isn't measuring the substance itself, it's measuring the concentration of those H+ or OH- ions floating around in a solution. And for that to happen, the stuff has to be dissolved, usually in water. No water, no solution, no pH reading. Simple as that.
So really, this is the key takeaway. It all boils down to this. The entire identity of an acid or an alkali comes down to which of these two ions it kicks out when it hits the water. Acids release H+, alkalis release OH-. That's the fundamental rule of the entire game.
Okay, so we've met our rivals, we know how to measure their strength, and now for the main event. What happens when these two opposites finally come face to face? This, my friends, is where the magic of neutralization happens.
Let's use a perfect everyday example you've probably felt before. Heartburn. That awful burning feeling, that's just too much acid in your stomach. So what do? You pop an antacid tablet? You're actually swallowing a weak base. Then, down in your stomach, the acid and the base meet, and they completely cancel each other out. They neutralize. And what are you left with? Two totally harmless things, a little salt and water. The fire's out. Problem solved.
And that, right there, is the textbook definition of neutralization. An acid and a base react. They cancel each other's powers out, and they form a salt and water. The pH of the whole mixture gets pulled away from those crazy extremes and heads right back towards that calm, neutral middle ground of pH 7.
And seriously, once you start looking for it, you see neutralization happening everywhere. It's in your toothpaste, fighting off the acids from the sugar you eat. It's what farmers do when they add lime to acidic soil so their crops can actually grow. And it's how we create tons of different salts that are used in everything from food to medicine. It's a reaction that's a cornerstone of our modern world.
All right, let's zoom out for a minute. We've seen how this works in our bodies and in our factories. But this whole acid-base balancing act is also absolutely critical for the health of our entire planet.
Okay, now check this out. This experiment from the source material is pretty fascinating. Scientists bubble different gases through water to see which one would make the water the most acidic. Now, you'd probably guess car exhaust would be the big villain, right? And it was pretty bad. It took 31 drops of an alkali to neutralize it. But then look at pure carbon dioxide. It took a whopping 160 drops. That is over 5 times more acidic than the car exhaust solution. So what on earth is going on here?
So why the huge difference? Well, the chemical principle behind it is actually pretty straightforward. When nonmetal oxides, and carbon dioxide is the classic example, dissolve in water, they react with the water and form acids. In the case of CO2, you get carbonic acid. It's just a fundamental chemical reaction that happens every time. And when you take that simple reaction and you scale it up to a global level, well, the consequences are enormous. This is the exact chemistry that causes acid rain from sulfur and nitrogen oxides when we burn fossil fuels. And it's the driving force behind ocean acidification. The source material says our oceans are soaking up about a quarter of all our CO2 emissions, and that is slowly but surely tipping their delicate pH balance, making them more acidic.
So this really brings us full circle, doesn't it? We started out in the kitchen with a lemon and a bar of soap, and we've ended up talking about the entire planet. But the story, whether you're looking at a microscopic level or a global one, is exactly the same. It is all about maintaining a very, very delicate balance.
When you get right down to it, this balance between acids and bases is what makes life possible. It's what keeps our bodies running, our soil fertile, our oceans stable. So the question this whole explainer leaves us with is a really big one. We are actively disrupting this fundamental chemistry on a planetary scale, and that forces us to ask a tough question. If we keep tipping the scales, what are the chances we can actually rebalance it?